Hello ICSC 2017 and all our fellow CSounders. My name is Dr. Gleb Rogozinsky and this is Eugene Cherny and Dr. Michael Chesnokov of Nuclear Resource Center, St. Petersburg, Russia. In this video we are going to tell you about the current status of a project called pch2csd, which is actually focused on simulation of famous synthesizer clavier not modular G2.
Let's start from the brief overview of a not modular editor interface. All modulars are grouped under 16 different categories. The oscillator section includes some basic, periodic, and also noise generators. There's also some physical models like OSC string and even famous Yamaha DX7 model. The input-output section includes basic outputs and inputs, and also a fixed input to route the signal to the FX part of the patch. The filters include few simple filters like low-pass or high-pass filters, and also some more elaborated ones. There's also a voice modeling filter, a 16-channel vocoder, and some equalizers, of course. The LFO section consists of several LFO generators of different complexities, and also there's a clock generator needed for any sequencing. There are several envelope generators available in not modular, including classic ADSR, and also some simpler envelopes and some more flexible ones, like multi-stage envelope generator. Shapers include different modulars for wave shaping, like clips and drives. Mixers include multiple kinds of mixing modulus to mix different signals. A fixed section consists of stereo chorus, phaser, flanger, digitizer, frequency shifter, pitch shifter, scratch simulator, the reverb, and the compressor. All the buttons and selectors are in the switch section. There are also several types of sequencers available in clavier, including small note sequencer. MIDI section includes typical MIDI-related models, like note send or control receive. The not modular patch consists of two parts: The VA stands for voice area, which is the subject of polyphony, while FX is a global FX part. I will demonstrate now the creation of a simple patch. Let's grab a simple oscillator, which will produce a sawtooth wave, and connect it to the output model, which is like C-sound outs. Notice that the A-rate signal is a red color cable. Please notice that Not Modular supports output-to-output connection. This feature made our work a bit more difficult at some stage. Now let's include a low-pass filter with resonance. So we feed a signal through the filter. Of course, we may tweak some filter parameters directly. Now let's use the LFO unit to modulate the cutoff frequency of our filter. Notice that the control rate cables in Clavier are blue ones. Now let's try some different thing. Let's bring up a simple decay type envelope and connect it to the patch. As you may see now, some models can change their behavior from audio rate to control rate and vice versa. Now we take a simple 16-step sequencer and then sync it to the clock generator. The yellow cables are used to route the impulses. The one-step rhythmic sequence now will trigger the envelope. Now let's delete the clock generator and try to retrigger the envelope using LFO. This is an example of type conversion. So the blue cable or control rate signal is converted to another control rate signal of pulses, which is a yellow cable. Finally, let's add some effects using global FX section. So we need to place a desired effect to the FX section and route the signal to it using FX in. This is the stereo reverb. So it was a brief demonstration of programming logic in Not Modular synthesizer. Now some words from my colleagues.
I mainly dealt with the problem of low-level parsing as a first stage of the project. Actually, we use the materials of our colleagues, but we not only investigated the structure of original patch files. We also created a converter that adapts the data to another format.
I joined the project later to contribute bug fixes and more features to the converter. But after tweaking around with the codebase for some time, I decided to rewrite it from scratch in Python. The old code worked well in general, except it missed some features, but it became hard to maintain with time. At the current state, our tool can parse binary patch files created by Clavius editor and generate the C sound code from specially prepared templates. Next, I'd like to demonstrate to you how the tool works in a screencast that follows in a moment. In this video, I will demonstrate you how our tool works and explain a bit of details based on some simple example. I prepared a very simple patch for you to just demonstrate. So this patch consists of a single saw oscillator, which volume is controlled by level amplifier. So, and then the sound just goes to the DAC. We can try to convert this patch using pch2csd command with just one argument. And as the first argument, you need to pass a path to the patch, basically. So let's do this. So yes, this is our new csound CSD file, and we can try to run it. So yeah, and let me show you how it works. So for this I will open the resultant CSD file and explain how it works. So we have a number of predefined variables like global variables. Also, we generate some function tables we don't currently use, except probably for the saw wave. And so after the static definitions, which come from the templates, go the UDOs, which represent each module, and the main instrument. So as you can see, our generated code doesn't look like typical csound code. That's because we don't use opcode returns and inputs to pass signals around. Instead, we use ZAC space, ZAC patching space, which we define somewhere in the beginning of the CSD instrument. And instead of passing signals from variables and somewhere else, we just connect modules internally. So each modules should have some opcodes that read from ZAC space or write to ZAC space. So yeah, basically this is it. And taking this particular example, we can see that our oscillator is the source signal. It has 2 inlets and 1 outlet. So these are 2 control inlets and one audio outlet. With this statement, we tell this opcode to read values from the ZAC space, from the ZAC bus 1 for these both inlets, and to output the signal to the 7th ZAC bus. So this one will be passed to the 7th bus. The thing is that 0 and 1 ZAC space buses are special. The 0 bus is a trash bus, so you basically can write anything to bus and it will just disappear. And the bus 1 is a bus which no one writes to, so you can safely just read from this bus, and you will be sure you always get 0. So this way we represent that there is no connection here. And then from the 7th ZAC bus, sound goes to the level amplifier, which happens to have one inlet and one outlet. So yeah, this is it. And this level amplifier outputs the signal to the ZAC bus 8, which then goes to the out 2, which has 2 inlets, and as you can see, it reads from 8th ZAC bus. So yeah, you just saw basically a description how these different modules got connected to each other. So in order to successfully convert a patch, you have to be sure that all modules that this patch uses are implemented by our tool or by you. So to implement the modules, you have to follow some simple rules, and the tool should work, the conversion should work fine. So the main issue here is the number of implemented modules. And we implement modules as opcodes. So one opcode is one module, which encapsulates all things that a module may have, like all the logic and everything like this. And also we introduced some annotations to help the converter to do its job. I won't go in too much details about this because we don't have time for this today, and just to get more information, you just consult our wiki page on how to create a new module, and you'll understand more probably. But I do want to outline some specific features that could be interesting here, at least at this conference. And so there are 2 essential types of annotation we introduced. The first one is the arcs annotations. This annotation helps the converter to determine how many knobs or other user interface parameters the module has, and also it helps the converter to determine how many inlets and outlets the module has, and also the types, what are the types of these inlets and outlets. So in this particular example of the level amplifier, we have 2 user interface parameters. As you can see, there is one knob and one switch, and we have one inlet and one outlet. The thing here is that a little bit complex thing here is that the modules can be polymorphic, like this level amplifier. That means that when, for example, this level amplifier by default accepts control rate signals, but as soon as we connect an audio cable to it, it changes its type. And unfortunately, C-Sound is not very expressive enough to represent all these kind of generics types of logic and things like that. So we went a kind of straightforward way, just to include two copies of the opcodes, which differ by the inlet and outlet type. And depending on what kind of patch cords are connected to this module in the patch, the converter chooses the appropriate implementation. So to wrap up, the arcs annotation helps us determine how many parameters the module has, and how many inlets and outlets, and as well as their types. Another annotation is the map annotation. It helps our converter to map the MIDI values that are stored that are stored in the patch to the actual values that can be used inside the opcodes. For example, in this particular level amplifier, we have a level amp table that maps from raw MIDI scale to some floating point scale, probably logarithmic and something like this. And one complexity here is that we can switch the scale of some parameter by some other button. And for example, here in the level amplifier, we have a switch that switches the scale of this knob from some linear to decibel scale. And our tool can also take these things into account, but as I said before, it will take too much time to explain everything in all these details. The last thing I want to mention in this particular screencast, we have a special page that is generated every time we build a project, and it contains a status of all implemented modules. By looking at this page, you can understand kind of how many modules are already implemented to some degree, and what modules need some attention, or maybe some of them are not implemented at all.
That's it, folks. Thank you for watching our video. I hope you enjoyed. If you want to join the project or help us, please mail us. Bye!